This is Reem. She just got a text from this guy in her class. She's trying to make an impression on him. She has a date with him tonight. She's lost. She doesn't know what to cook. She wants to switch things up and not cook her ordinary burnt pasta. Therefore, she's looking around in her fridge and her pantry, but she has no inspiration. Fortunately, she can find the solution to her problems thanks to the simple touch of a screen. Hey guys! Have you ever wondered how you could switch things up in the kitchen? If yes, then keep on watching. Get ready, because you're in for a ride.
Cooking is an activity that brings everyone together because we all have to cook in our life, regardless of our age or our social condition. When we cook, we do things that seem logical to us, like mix or bake or boil, and we never wonder why are we doing so as long as our final dish is successful. However, humans are curious, and with more reflection, we could be brought to ask ourselves why are we doing so and how can science explain that? Because science can't explain a lot of things, but cooking isn't one of them.
Therefore, molecular gastronomy is a way of using science to master and understand cooking. The base of molecular gastronomy is the study of chemical reactions between foods in order to make creative meals. Smoking dishes, bubble-shaped carrots, that's what you can find on your plates these days under the name of molecular gastronomy. Favoring both appearance and flavor, it aims to go further and further in the imagination of new tastes and especially new textures. To sum up, molecular gastronomy is a perfect compromise between science and art. So now, before getting into the details, let's get a trip back to the 1980s to find out more about its beginning.
Molecular gastronomy owes its name to Hervé Thys, a French chemist, and also to Nicolas Curti, a physicist from Oxford. The term of molecular gastronomy had its first apparition during a meeting in the 80s. This idea of molecular gastronomy sparked because Hervé Thys thought that the traditional way of cooking is outdated, even medieval, to use what he said. Indeed, he is a chemist but also a physicist, so he studied the working of hot plates, and he realized that almost 80% of the energy supplied by the hot plate is lost and therefore not received by the pan, so he decided to find a solution. The solution he found is to create a new way of cooking by using new utensils and new methods. These methods are based on science, in particular on chemistry, because the study of chemical reactions in food allows to reap all the benefits of the food.
The main source, the main objective behind molecular gastronomy is this desire to renew this ancestral form of art that is cooking. Analyzing and studying the chemical properties of foods and the reactions between them makes it even easier for scientists, for chemists to improve existing foods and to create even new ones, or even to combine naturally non-combinable and non-miscible ingredients. An example of that is one of Hervé Thys's molecular gastronomy creations, that is a liquid nitrogen ice cream. Now, you might have not heard about that, but I'm sure you've heard about the second example, that is mayonnaise. It's one of the world's most famous condiments. Mayonnaise is actually a form of molecular gastronomy, as it is the combination of naturally non-miscible ingredients that are oil and water. Molecular cooking can also be useful in big-scale food production. All colorants, additives, and preservatives are actually the result of chemical researches done to improve the quality and the performance of foods. Now that we've talked a bit about molecular gastronomy, it's time to see the different techniques used in it.
Today, the greasy chefs like to offer on their tables dishes with futuristic connotations. The 5 major techniques of molecular gastronomy are gelling, spherification, thickening, emulsifying, and dehydration. Once mastered, liquid nitrogen ice cream, Coca-Cola beads, pistachio sponge, or whatever, it will have no secrets for you. Now, we are going to briefly explain these 5 techniques. Let's start with gelling. Gelling is the oldest technique in molecular gastronomy. This technique results from the transformation of a liquid into a gel thanks to proteins. These proteins may come from animal, vegetables, or from agar-agar. Then, spherification. Spherification is the art of turning a liquid into a sphere. The spherification can gel daily ingredients and dishes in a form of little ball.
Another technique of molecular gastronomy is the immersion. Immersion is the mixture of 2 immiscible products that normally don't mix. There exists also thickening, which is the action of increase the density of the liquid. Thickeners used in molecular gastronomy make the sauces creamier without altering tastes. The 5th technique is dehydration. It's the action of removing water from food. So, in this video, we choose to talk about spherification and immersion.
Spherification was invented in 1942 by British food scientist William Peshert. It is a technique that consists of wrapping a drop of liquid in a solid membrane. This process is used amongst others to make caviar. The consistency of these small little spheres is very satisfying because once you bite into them, they reveal all of their delicious flavors. Here, we are going to use calcium alginate extracted from an algae. It is also known as agar-agar. Now, you may be wondering, what is agar-agar? Well, agar-agar is a gelling agent extracted from an algae. It is mainly manufactured in Japan and it is sold in a powder form. It does wonders in molecular gastronomy, like in spherification, or as we've seen before, in jellification.
Sodium alginate is mixed with the liquid you want to spherify, for juice for example. The mixture is then transferred to a bowl containing calcium chloride solution. As soon as the droplet of alginate and the liquid you want to spherify meet the calcium chloride solution, it forms a sphere with the liquid inside. From a chemical point of view, the reactions of this process are fascinating. When sodium alginate is poured into a solution containing calcium ions, each calcium ion repels 2 sodium ions, because these 2 ions are both cations. In French, we call this force répulsive. In addition, the alginate molecule contains many hydroxide groups that can be bound with cations. When alginate is bound with sodium, it forms a very flexible chain. But when alginate sodium transforms into calcium alginate, each ion is related with 2 chains of alginate, binding them together. Chains become less flexible and form a vast network which form the skin that envelopes the liquid. By the way, the balls have a spherical shape because this shape is the one that requires the least energy. Now guys, stay tuned. We want to show you a little experiment that we have made for you. Hope you like it and try it at home.
First, you're gonna start off with 10 centiliters of raspberry syrup or any kind of syrup.
Then, once that is done, pour it in the pan.
Next up, you'll need 10 centiliters of water.
Mix your water with your syrup, and to this mixture, add 5 grams of agar-agar.
Bring your mixture to a boil.
You'll start noticing small white bubbles on the surface.
In a cup, pour some cold oil of your choice.
Now, with a syringe, drop slowly the mixture into the cold oil.
If you look at the bottom of the cup, there should be small spheres formed.
Following that, with the strainer, remove the oil and collect the small beads.
Wash the beads in water to remove the excess oil.
The oil that you use must be cold, or your experiment will fail.
Once all the steps are done, plate it up in the fanciest way possible. Then the caviar syrup is ready to be enjoyed. Bon appetit!
Now we are going to talk about emulsions. Like we said, an emulsion is a more or less stable mixture between two products that are normally not miscible. In molecular gastronomy, it's not only used for that, but also for creating mousses. Usually, we mix an oily solution with an aqueous solution, and the mixture obtained is divided into phases. The first phase is a discontinuous phase, and it's divided into droplets in the second phase that is not discontinuous, so it's continuous phase. The emulsion has to be stabilized by an emulsifier. The most common ones are gelatin, lecithin, or phospholipids. An emulsifier has to be hydrophilic, that means it has to mix, to combine, to be attracted with water, and it has to be lipophilic too. It means that it has to mix and to dissolve in lipids or fats. There exist three different types of emulsions: the direct emulsion, the reverse emulsion, and mousses. So the reverse emulsion is the opposite of a direct emulsion. The continuous phase, that is the aqueous phase in a direct emulsion, becomes the discontinuous phase, and the oily phase, that is the discontinuous phase in a direct emulsion, becomes the continuous phase. For mousses, the discontinuous phase is replaced by air bubbles. In our video, we choose to talk about a direct emulsion by developing the example of the mayonnaise. Because in mayonnaise, there is a direct emulsion between water and oil.
For the picture on the right, we just poured in a glass some oil and water to see if those two mix. Spoiler alert, they do not. We can see that oil has a tendency to stay at the top. Then in the second picture, we stirred this mixture. We can still see two very distinguishable phases, with the water at the bottom and the oil at the top. Therefore, we have to stabilize this emulsion. We have to add to the mixture a molecule that has an affinity with both liquids. That type of molecule is called surfactant compound, des tensioactifs. First off, the water molecule. The water molecule has no electric charge. Indeed, it is formed of an atom of oxygen that has a negative charge that is counterbalanced by two atoms of hydrogen that have a positive charge.
Oil molecule is composed of three long carbon chains made by fatty acids linked by a molecule of glycerol. The triglycerides make the majority of the dietary lipids. This molecule is characterized by its insolubility in the water and its apolarity. The surfactants, in French, tensioactifs, To mix oil and water, a molecule has to be introduced into the solution. A molecule that has an affinity with water as well as with oil. They are amphiphilic. The head is hydrophilic and the body is hydrophobic. The head is attracted by water, whereas the body is attracted by oil. That means that the surfactants allows the mixing of oil and water.
What to take away from this video is that molecular gastronomy offers a wide range of techniques and methods to improve everyday cooking. You can realize a lot of recipes with these new methods.
Did you enjoy this video? If yes, then sign off, get up, and start cooking. Now that Reem finished watching this video, she has a lot of ideas for her date. We hope she's not gonna burn her apartment down because she has the idea. She has the intention, but she still lacks the talent of cooking.